So today we're going to continue chapter 3 and we're going to finish chapter 3 and we're going to transition to the second half that has to do with floating point number representation in binary. And the idea here is that in the first half we were looking at integer representations, and a lot of that plus the logic design of the multipliers could have been a little bit of a review, but I believe this information that we're going to present today is mostly new, at least to most of you. So we're going to talk about floating point representation and the benefits of it, because we still have a fixed storage in the word of this number of bits, and we could have assigned certain number of bits to represent the fractional part of a number, and then another number of bits to represent the integer part of a number. And that may work somewhat, and it's actually done, because as we'll see, the hardware complexity of floating point arithmetic is much higher than that one of integer based arithmetic. So there is a benefit of using what is called fixed point format, which, like I said, is you assign certain number of bits for the fractional part, you assign certain number of bits for the integer part. And it ends up looking to the hardware like it's just integers, okay? But there are limitations, although there are applications that can work with that. In general, is very restrictive. So we're going to need a way to represent numbers in general that have a fractional part, as of course an integer part, but in a very in a way, in a format that is very that lends itself to represent very small numbers, very large numbers, and so forth. So that's what we're going to start talking about today, which is the floating point format, which is like scientific notation that we're all familiar with. So essentially, a number is represented first normalized according to certain rule, and then that number, that normalized point number, is multiplied times a base raised to an exponent. Now for us, that's the base 10, because that's our base, the base that we count on. And but for computers, since everything is binary at the hardware level, we're going to look at a format that is uses a base of 2. So the format is going to look something like this. First, we're going to need to represent the sign, and we're going to see that the format uses what is called sign magnitude, which is 1 bit for design, and the number after that doesn't change. Whether it's negative or positive only depends on that 1 bit, but the number is always the same, it's the magnitude. Then then that number is going to be normalized such that we have a 1 point something, okay, a fraction, and that is going to be in base 2, in binary, and that is going to be multiplied times the base, which is 2, raised to an exponent. And there are some interesting things about the exponent. There is a bias also that we're going to be introducing. One thing to notice is that if we normalize the number to 1 point something, that 1, we don't have to include it. We don't have to include it in our number because it's always there, it's implied. And we gain 1 more bit to store more fractional bits and give us more precision. Okay? So if we had this number, okay, how would that look in binary? So that's an exercise for you to do after we finish the presentation. So the floating point standard is an IEEE standard. So, and it was developed to homogenize, to standardize the way that software developers, compiler developers, and chip developers, processor developers were responding to the way that they were dealing with this type of representation. Okay, and we're going to see that there is a single precision variation, which is 32 bits in length. There is a double precision. We're going to see both of those, single and double precision. There is also a quad precision of 128 bits that is mostly used in gaming, but we're not going to cover that here. And we're going to see that when you have a standard, the complexity of standards come from trying to create a response and address the corner cases, the exceptions, and things like that. And as we're going to reiterate towards the end, most everybody covers 90% of the standard and is straightforward, although you're going to see that it requires a lot more hardware than integer arithmetic. But what makes it complex is really covering all this, the different types of exceptions that you can have. And we'll talk about that some more later on. So this IEEE standard for floating point format is basically everybody uses it. So you need to know it and be aware of it because when something is standardized, there are clear advantages that you simplifies the exchange of data, simplifies the arithmetic of algorithms because now you can represent, as I mentioned, very small numbers as well as very large numbers, and that increases the accuracy. And sometimes you need more accuracy than single precision, what single precision can provide. So just so you know, it doesn't take that much to go over the precision that single precision can provide. It's about 6. It turns out to be about 6 decimal points that you can represent with single precision. If you wanted to represent more than 6 decimal points, then in a lot of applications it's necessary, you need to go to double precision. And once you run out of precision there and range, then that's why we have a quad format, although we're not going to be covering it in detail. I'm just mentioning it. So let's take a very detailed look at how the format works for both single and double precision. So imagine that this is the word, the data path word, and is either 32 bits or 64. The most significant bit is always the sign bit. If it's 1, the number is negative. If it's 0, the number is positive. Then you have 1 plus the fraction, so that gives you the 1 point something. And since the 1 is implied, we don't have to store that 1. It's always there. We just have to store this fraction. And we're going to store it in the lower or the least significant bits. And then that is going to be multiplied times 2 raised to the exponent bits, which are here in the field between the sign and the fraction, minus a bias, okay, which is different for each, the single format and the double precision format. So if this is the data path word, we always have 1 bit here for the sign. If we have single precision, the exponent is limited to 8 bits. And if we have double precision, then the exponent is 11 bits. For the fractional part, if we have single precision, then the fraction is represented with 23 bits, and for double precision, the fraction is represented with 52 bits. Okay? So that is if you know the exponent, if you know the fraction, you can apply, and the sign, of course, you can apply this equation to get your decimal floating point number or fractional number and the integer part. And you also need to know the bias, what that bias is for both the single and the double precision. So for single precision, the bias is 127. And for double precision, the bias is 1023. This is a typo here, okay? The numbers in the middle are reversed. It's 1023. What that does is that the exponent, because sometimes you're going to want this expression here to be negative, and sometimes you're going to want that expression to be positive for small numbers and large numbers in your range. But by having a bias that you subtract, it makes it so what you store is always a positive number, because when you translate it, you are going to subtract the bias. And having the exponent be always positive is very desirable because it lends itself to make implementation of sorting algorithms easier, because you don't have to be looking at negative and positive numbers. The exponent is always positive where you store, even though what it means is a negative number sometimes if it's below the bias. Okay? So that is the motivation for using a bias. So let's look at the range a little bit, okay? For the exponent, we have this number of bits, 8 bits. Now, the other thing that you can have with floating point format is not only overflow, which means that the number is too large to fit in the storage that we are assigning to it, either 32 or 64 bits, but also you can have underflow, which means that the number is too small. And again, the hardware has to take care of at least detecting these conditions. So how does it work for the actual number, the representation of the exponent? So the smallest value that we can have for single precision is when an exponent is 1, because 0 and all 1s are reserved by the standard. So this is the smallest number that you can put in the exponent bits. So when we subtract the bias, then the smallest exponent is minus 126. Okay? And then the lowest fraction that you can have, is all zeros, which is the number 1. Because remember that this 1 is implied, which is the number 1. So that gives you a range, because 2 to the minus 126, and when you apply that, is that the range is plus or minus 1.2 times 10 to the minus 38. That is the range of the, or the smallest value, the smallest value that the single precision can take into account, can represent. Now let's look at the largest value. The largest value is when the exponent is this binary pattern. All ones except the least significant bit is 0, because remember that all ones is reserved. So that is 254 minus the bias 127. So that gives you an exponent of plus 127. And then the fraction is when the fractional bits are all ones, which is 1.01, which is almost 2. So the largest value is this over here, which in decimal is plus or minus 3.4 times 10 to the 38. So that is the largest value. Now let's look at it again in the double precision format. Do the same, go through the same thing. And again, all zeros and all ones are reserved. So the smaller exponent is 1, and the bias is 1023, as I mentioned. So the most negative exponent as a power of 2 is minus 1022, and the fraction is all 0, so that's 1. So that gives you plus or minus 1 times 2 to the minus 1022, which is plus or minus 2.2 times 10 to the minus 338. I mean, 308. And same thing for the largest value, when the exponent is all ones except the least significant bit. That is 2046 minus the bias, that's 1023. And then the fraction also is all ones, which is again almost 2. And that gives you plus or minus 1.8, about plus or minus 1.8 times 10 to the 308. So that gives you an idea of the range for both the single precision and the double precision. So it's you can observe that by doubling the number of bits in base, that's the equivalent in base 10 to increasing the range about 10 times. So you go from plus or minus 38 to about plus or minus 308. Not quite 10 times, but almost. That's just an observation. So what that means is that, as I mentioned, that when you look at the precision of what the fractional bits can encode, the single precision gives you about 6 decimal digits of precision, and the double precision gives you about 16 decimal digits of precision. And that's important. This is important to remember, because if you are coding in C++ and you know that you are dealing with numbers where you need more than 6 decimal digits, then you need to define your data as doubles instead of floats, which is in C++, float is the single precision and double is the double precision. So the standard calls for dealing with what is called denormal numbers, which these are the smaller than the normal numbers that the standard can allow for. Also, the standard calls for how you deal with the fact that you can have 2 representations for 0, because again you have the sign bit separate from the actual the actual number, the actual magnitude. And what we're covering here in this chapter is essentially 90% of the standard. How to go from one representation in binary to the actual decimal representation and vice versa. But you just need to be aware of these exceptions and corner cases. The standard also covers things like infinites and what are called nans, which are not a number. Essentially, you can come up with a result that doesn't make sense as a number. Okay, but you can have plus or minus infinity, and the standard allows for encoding that. That's when the exponent is all ones, that's why it's there, and the fraction is all zeros. But if you have the exponent as all ones and the fraction is not equals to all zeros, this is what is called not a number. And it indicates an illegal or undefined result. So your arithmetic needs to check for these cases and produce these results that are well understood according to the standard. For example, if you get 0 divided by 0. And then those results can be used by subsequent software to take appropriate action, because the meaning and how you got there is well defined. Now let's look at the actual arithmetic, and you'll see why the arithmetic units end up being more complex. Let's just consider a 4-digit binary example, which is not a standard, it's just that it's more manageable to talk about it here. How do we do addition if we had this number 1.000 times 2 to the minus 1 plus minus 1.110 times 2 to the minus 2? So that turns out to be 0.5 plus minus 0.4375. Well, if we want to do addition, what we must do is align the binary points in this case, or the radix points. Now this and what we do is to shift the number with the smaller exponent. So we end up with 1 over here times 2 to the minus 1, and then minus 0.111 times 2 to the minus 1. Essentially, when we do addition, what we want to do is make sure that the exponents are the same, so they can factor out, and then we add the fractional parts, or the floating, not the floating point parts, but the 1 point fractional part, and then we just multiply by that exponent that we factored out, and we may renormalize again. So these significant parts here, once we have made the exponents the same, we can add them. So 1 plus minus 0.111. Okay? And that is going to give us 0.001 in binary times the same 2 to the minus 1, because it just factors out. And then we normalize again, because remember we want 1 point something, and we, in the process of normalizing, we adjust the exponent. So this number over here becomes 1.000 times 2 to the minus 4 And what we're going to see is that the arithmetic unit has to check for that overflow or underflow. You also have to round and renormalize if necessary. Again, the arithmetic unit for floating point numbers have to do that as well. In this case, we have no change in our example. So if you think in terms of hardware, how a floating point adder would look like, according to the steps that we went through, it would look like something like this. Now keep in mind that if we were just adding these two numbers as integers, I would only need just a big adder of as many bits as these words are. But it's just an adder, which is just one part over here. No need of control, no need of shifting. So what do we have here? Well, here we have a smaller adder or subtractor, which is going to figure out the difference in the exponents, so I know which one to shift. Okay? So these exponents over here both come to a multiplexer, and then depending on the difference, the controller select which one is the one that is going to go on and get shifted. And then it's going to become the exponent, because remember, they are going to be the same after the shifting. And then we're going to bring the fractions, which are going to be, so sorry about that. The exponents are not going to get shifted. They're going to be retained, but the fraction is the ones that are going to get shifted according to the difference in the exponents. That's what I wanted to say. So the controller is going to look at the difference and is going to know which fraction needs to get shifted and let it through to this multiplexer, and then is going to shift it as much as it needs to according to the difference. Okay? And then the other one is going to come through this multiplexer, and that's where they get added over here. So either of these fractions could be in a position to be shifted. So that's the one that is going to come this way on the left, because that's where we have the shifter. The other one is going to come the other way. And that's why we have the ability through the multiplexer to put either one of them through either path into the big adder over here, which is going to end up adding the fractions. And the idea, we call them ALU instead of adders, because we could do subtraction with this same hardware as well. Okay? Then this hardware over here is to do the normalization, where we're going to shift left or right the result and increment or decrement the exponent that we retained to do the normalization. So the controller essentially controls those operations by getting the information on the actual result, so it knows how much it needs to shift, right or left, and how much to increment the exponent by or decrement it. And then that result goes into the rounding hardware, which again rounds and renormalizes. And after that is when we get the actual fractional part, the exponent, and the sign that we of our result. So this is just to show an idea of the relative complexity of floating point arithmetic hardware versus fixed point arithmetic hardware. Going on to the multiplier, so similar relative complexity to the floating point adder, but it uses multipliers instead of an adder, of course. Okay. So what you can see is that, and what you see in the implementation is the floating point arithmetic hardware. They usually do a number of operations, not only the addition, but they do the addition, the subtraction, multiplication, division, and some functions as well, such as square root. They can also take on producing sine and cosine type functions and logarithmics and things of that nature. And they can also do floating point to integer conversion. This, no doubt, is going to take several cycles of the CPU. You don't want to constrain the frequency of the CPU by how long the floating point takes. So it's going to take several cycles, and usually it's pipeline. And you're going to understand what that is in chapter 4. So we can speed up the throughput, again, the throughput of completion of instructions. Now let's look at how the Leg 8 ISA addresses floating point from an architectural perspective. The ISA calls for separate floating point registers. So the register that we have been looking at are the integer registers. So it calls for separate floating point registers in the implementation. 32 single precision, 32 double precision, and the single precisions are essentially the lower part of the double precision registers. Okay. The set of floating point instructions in the ISA operate only on the floating point registers. Okay. So you cannot steer, and remember, when you think about the actual implementation, there is a lot of data steering through multiplexers that the controller of the CPU have to make happen. You don't steer integer registers through the floating point arithmetic unit. So they only operate on the floating point registers. Okay? And then there are appropriate floating point loads and stores instructions. So for single precision, load, single precision store, double precision load, and double precision store. So again, everything starts with the ISA. In this case, we show you the implementation of an adder first, just to give you an idea. But everything starts with the specification of an ISA, and then you have to implement that ISA support. These are some of the single precision arithmetic instructions. So floating point add, single precision, subtract, single precision, and multiply, single precision, and divide, single precision. So you could say floating point add, single precision, these two single precision registers, and the result goes in this single precision register. There is also double precision arithmetic. So add, subtract, multiply, and divide. And you could have, for example, this instruction, a floating point double precision addition of double precision registers 6 and 4, and the result going into double precision register 2. There are also comparisons for both single and double precision. And these comparisons have the effect of setting or clearing a dedicated floating point condition code set of bits. And then there is a branch on this floating point condition which can branch according to if the condition code is set or reset or true or false. So let's look at an example with of C code compiled into leg VA code, and this function converts a Fahrenheit number to Celsius. So the argument is a floating point number, which is some Fahrenheit temperature, and it returns the Celsius equivalent. And let's assume that the argument is in single precision register 12, and we're going to deposit the result in single precision register 0. Okay? So the first thing is that we are going to, because the constants, this is what literals are, is just a fancy name for constants, are in global memory. So here we're going to, we're assuming here that the base of this section of memory, where we have these constants, is stored in register 27. Notice that this register here is an integer register, because it doesn't make sense to use a floating point register when you're talking about memory, which is clearly integer, the addressing of the memory itself. And this is using the addressing. And this is the displacement, some label that is going to be the displacement, what the constant 5 in floating point is. And similarly, we have a displacement for the constant 9 in floating point. So all what this instruction is doing is loading the floating point 5 into single precision floating point register 16. And the second one here is loading the floating point value 9 into single precision register 18. Then this does the division, 5 divided by 9, because we loaded in these two registers, and we put that result in single precision register, floating point single precision register 16. Then here we're loading again another constant with its displacement, floating point value 32, and we're going to put it in register 18. Clearly, we don't need 18 anymore because we already did the division, so we are reusing it. Then we are subtracting the argument, which is in register 12, and we're subtracting 32 from that and putting the result in register or floating point register 18. And at that point, we have the argument minus 32 over here. And then what we have to do is multiply times that fraction 5/9, which we stored in register 16 over here. So we multiply floating point register 16, single precision, and floating point register 18, single precision, and put the result in floating point register 0, single precision. That's what we wanted the result. And we branch according to the link register, and we return to the section of code that called this function. So that's an example of how single precision arithmetic would be done. Clearly, these are single precision because we have float. We have declare, the declarations are float. If the declarations were double, then we would be changing everything to the double precision instructions and the double precision register set. You can have another set of code. So here's code to do a matrix multiplication with double precision elements, and the matrices are 32 by 32 elements. So you are taking three matrices, X, so this is a two-dimensional array of double precision numbers, X, and Y is another two-dimensional array of double precision numbers times another two-dimensional array of double precision numbers, and you're doing essentially X plus Y times Z matrix format, and you're putting the result in the same storage or the same two-dimensional array where X was. So if you look at the code here, matrix multiply, you're essentially passing the 3 pointers, so you don't need to return anything. You're passing the 3 pointers, and you're doing the arithmetic, the matrix arithmetic that does this matrix multiply, accumulate. Essentially, this is what is called a MAC, a multiply, accumulate, because clearly you're putting the result in X, which is acting as an accumulator in this case. Additionally, we're giving the information that the addresses of X, Y, and Z, the pointers, are in these integer registers, and that the values of I, J, and K are in these integer registers. Those are indices, so they can be integers. And this is how the code would look. Which I'm not going to go through it because it is straightforward, but it's lengthy. So I'm not going to go through it, but you will get the slides later on today, and you should go through it. So in terms of accuracy, some final notes that there is rounding control that the standard specify and extra bits of precision. So when I show you that adder, the width of that data path is actually wider than what the standard calls for, either for single or double precision, depending on what that is, but it's more. It's either more than 32 bits and it's more than 64 bits in the case of the double precision, because the standard calls for extra bits of precisions that are called guard, round, sticky. And these are the specifics of the standard that not everybody can take into account when it's implemented. So, but the bulk of the standard, how you go from binary to the decimal and vice versa, that's well understood, and everybody implements that. So the standard through these bits gives the programmer the ability to fine-tune the numerical behavior of the computation by having a choice on how rounding is done. Okay? And again, these are the more specific complexities of the standard that not all floating point units implement all these options. Okay? And what happens is that the implementations they just use the defaults because there are especially in the embedded market and microcontrollers, high-end microcontrollers that are starting to have more and more floating point arithmetic units. There is a trade-off between complexity, the performance, the cost. So not everybody implements that. But if you were going to actually read the standard, you will find that we have all these different nuisances that can be dealt with as part of it. Now let's, I mentioned this in last time when we were talking about integer level, because remember that graphics and audio don't need sometimes a lot of precision, specifically video and imaging does very well with 8 bits. Audio can do very well with 16 bits and so forth. So you end up with the ability to use wide arithmetic units that you have implemented to do other type of applications like data processing, things that are dealing with the specific computations, with finance and things like that, that you need a very high level of precision. Scientific computation, you may need a very high level of range and precision both. But if you are trying to implement software for an application that is related to multimedia, then you don't need all that. And what can be done is to repartition those wide arithmetic units to do multiple computations at the same time by reconfiguring the arithmetic units. Because what this multimedia type of applications do require is the ability to do a lot of them in parallel as fast as possible, because usually there is a streaming aspect to the application, whether you're streaming music, whether you're streaming video. So the idea is not to get a lot of precision necessarily, but how to do high throughput. And even if you don't get the right value because you have saturation, as we explained last time, that's not so important as the ability to get data there, some data, and keep things going, keep the frames moving, both for audio and video. So that's what happens when you have the ability to repartition these wide arithmetic units into subword and do what is called vector processing. So how does the ARM, again, we're always going back to the ISA, how does the ARM addresses vector processing? So we have another set of registers. Again, how much of this is implemented depends on the actual implementation of the processor. And you have to communicate this whether you're living in a high-end type of application or a lower-end type of application. You may not do floating point. You may not do vector processing, but the ISA defines this as a matter of specification. So it defines 32 128-bit registers. So V0, the vector set of registers, V0 through V31, and they work both with the integer set of registers and with the floating point. Okay, so then you have this vector type of operations. So if you wrote add v1 dot, and this is the notation for vector for the vector addition, v1 dot 16 b, and here you have v2 dot 16 b and v3 dot 16 b. So that means that you're going to do in these vector registers, remember that they are 128 bits. So you can fit 16 bytes in 128 bits. So you're going to do 16 additions at the same time on bytes. And each respective byte of vector register 3 is going to be added to the respective byte of vector register 2, and the result is going to be put in the respective byte of vector register 1. Because each of this is 16 bytes. But the 16 additions of 8 bits is going to be done at the same time. A 128 bits also can fit 4 32-bit or single precision floating point values. So you can do 4 floating point additions at the same time in a vector manner. So again, the appropriate 32-bit in vector register 3 is going to be added to the appropriate one or the corresponding one in vector register 2, and the result is going to be put in vector register 1, because in each vector register we have 4 single floating point values of 32 bits, of course. So that's the idea behind vector arithmetic, and also in the context of the relationship with the floating point part of the ISA. Now remember that this is the actual, this part of the ISA that we're talking about is the actual full-fledged ISA of the ARM version 8 ISA. It's not the leg that we are discussing in the book. So the this ISA specifies 245 vector type instructions. So a square root, multiply, add, sort of the multiply, accumulate, or multiply, subtract. The conversion from a scalar and vector to integral or to integer. You can also add and store these vector registers all at the same time, and also the important part, the saturating arithmetic effect, where if something is too large, you don't necessarily signal an overflow, but you saturate at the highest value. And that, as I explained last time, that makes sense for data that is going to be consumed by human senses, either vision or hearing. And if you have something too small, then you just saturate it at the lowest value, usually 0. So that's part of the instructions that are more geared towards multimedia processing. Now, as we end the chapter, we'd be remiss if we didn't talk a little bit about the Intel story. And back when the 8086, the first Intel processor that became really popular with the PC, the birth of the PC, there was a floating point coprocessor, which is actually a separate chip that you would put on the motherboard, and that was called the 8087. Just to give you an idea, it had about 8 80-bit what they call extended precision registers. The actual implementation architecture was a stack architecture, okay, where registers were indexed from the top of the stack, and the values were taken from memory. So to get to the values back to the master processor, the 8086 in this case, had to go through memory. And anyway, it was as it would be when you have two different chips trying to do this. Is the performance was poor, so it really didn't. The PC didn't have a good floating point performance until they were able to integrate the floating point with the processor in this on the same chip, for obvious reasons. There is an important story about an actual bug that the Pentium floating point division instruction had that actually made the news in a very big way. And this is the best place to find this is in the Pentium Chronicles. It's a pretty entertaining book. But that made a lot of news a few years ago, quite a few years ago.